Good morning, students. It's Monday, 5/11/2020. Can't believe how fast things are flying by. I know some of you, the time is just creeping by. Stay busy. Try to learn as much as you can. Occupy your time with learning things. Nothing better than that. All right. Today's video is going to be pretty short. What do I want you to do? I can list some factors that affect the melting point of rock. I can describe some visible differences between intrusive and extrusive igneous rock. Okay, so definitely some vocabulary there that we're going to have to get down, and then I want you to be able to describe what you would see. So, all right, let's think about this. Igneous rock forms when magma or lava cools and crystallizes, right? So the crystallizing is when the particles come together and line up in a nice pattern, okay? So in order to get igneous rock, we got to get magma or lava first. So magma and lava are molten rock, melted. What are some factors that affect melting? All right, well, one is temperature. You, I think, know that it takes heat to melt stuff, okay? Now, within the earth, temperature tends to increase as you get deeper within the earth. So the deeper you go, that's giving you more chance of having enough temperature to melt stuff. Typically, we don't find a whole lot of melted rock on the surface of the earth. Once in a while, there's a volcano where it comes bubbling up. So the higher the temperature, the more likely it is for something to be melted. That makes sense. All right, pressure. That's one we don't think about as often. Now, pressure is this squeeze holding stuff together. And when you squeeze materials together, it tends to want to keep them in a solid form, because in a solid form, that's where the molecules are packed as tight as possible. So pressure tends to not let things melt. Now, pressure increases with depth in the earth. We saw that temperature increases with depth in the earth. As the temperature increases, you have more chance of melting. As the pressure increases, you have less chance of melting. So those two factors, as you go in the earth, fight each other. And that's why deep in the earth, most of the earth is solid, okay? Most of the earth is solid rock. There's only places where the temperature and pressure conditions are just right to give a liquid. That's not a common thing. There's places, but it's not like, you know, I used to think as a kid that if you just dug deep enough, it gets hotter and hotter and everything would be melted. That's not really true. All right, what else can happen? Water. If there's water mixing in with the rocks and minerals, it actually tends to make it easier to melt. So when we have mixtures of things, they sometimes melt easier than just the rock by itself would. Okay? And then, of course, composition is referring to what is the rock made of. I don't think it's too hard to accept that there's different types of rocks. There's different types of minerals that make up our rocks. And different substances have different melting points. Just think about in your house. You know, it's a wax candle melts pretty easy, just a little bit of heat. But a copper frying pan, steel frying pan, or aluminum frying pan, those don't melt nearly as easy. It takes a much different temperature to melt a piece of aluminum than it does a piece of wax. It takes a much different temperature to melt a piece of copper than it does aluminum. I've played around a little bit. I built myself a home foundry, and I've done some aluminum casting. And I can melt aluminum fairly easy with a wood fire. I haven't tried doing copper or anything else yet, because I know that to melt copper takes quite a bit higher temperature, and I'm not sure if my fire can handle that. It's just different materials have different melting points. Well, within our ground, different rocks, different minerals are going to have different melting points. So how do we get magma or lava? If we have the right type of rock under the right temperature and pressure conditions, we can get magma or lava. We talked about in the previous chapters with plate boundaries that if you have a divergent boundary where the plates are spreading apart, when the earth cracks open, it's reducing the pressure below. So you had hot rock below, but now you take some of the pressure off, allows it to melt. We talked about at convergent boundaries where when one plate is subducting underneath another, it drags along with it water and sediments, changing the overall composition, and that stuff melts easier. So these are all factors. I would want you to be able to repeat to me what are some factors that affect melting. All right, so we classify igneous rocks in two ways, and they're referred to as extrusive and intrusive. Relate those words to other words that you should already be familiar with. Think about what's the interior of your house? Well, that's the inside. What's the exterior of your house? That's the outside. Okay? Extrusive igneous rocks form outside the earth. Intrusive igneous rocks form inside the earth. So let's imagine we have magma. I'm going to actually start with the inside of the earth. So here's my earth. If I have magma, a magma chamber in the earth, okay, and so something happened that was able to melt that rock, turn it to a liquid. And now, let's say conditions change, and so that magma chamber slowly cools off. Now, I say slowly because in the earth, temperature doesn't change real fast. So, as that cools off, that liquid particles are going to start to line up with each other, crystallize, and form back into a solid. That's going to tend to be a rather slow process. And when it's such a slow process, sometimes those crystals are able to grow very, very large. Intrusive means inside. Interior means inside. Intrusive igneous rock forms inside the earth. All this granite that we have right here in Marathon County, we pave our driveways with it, we pave our roads with it, not the big highways, but you know, the back roads, and all of you are familiar with that. That rotten granite is an intrusive igneous rock. There was volcanic action here billions of years ago, and there was magma under the ground that slowly cooled, turned into rock. And that particular crystalline structure of that rock has broken down a bit over time, and that's where we get this crushed, rotten, broken up granite. So extrusive, we're going to have a volcanic eruption there. The magma gets pushed out. Now it's called lava. And now when you have rock at several hundred, maybe over 1,000 degrees Celsius, hits air at 20 degrees Celsius, it cools very, very, very quickly. And so what happens there is, because it cools so fast, the crystals are very small. So extrusive igneous rocks, the crystallization happens outside the earth. Extrusive, exterior, outside. Tends to have small crystals. Now I got a couple of samples here, and I'm hoping that you'll be able to see, if I hold it still, you can see on this rock, you can actually see the different crystals. You can see there's different colors and different textures, different shininess. Those are different crystals. And what that means is that this rock cooled relatively slow. This piece of rock just looks kind of a uniform gray, and with just my eye, I really can't make out any individual crystals. Maybe through a microscope, we might be able to see it. I'm guessing that rock cooled very quickly. I have another one that looks like I can see little bits of crystals. They're smaller than the first I showed you, but bigger than the second I showed you. So again, I'm thinking the rock, they have different rates at which they cooled off. I am not a rock expert by any stretch of the imagination, but with my limited knowledge, I would definitely think that this is an intrusive igneous rock. Okay, looks like a piece of granite. Granite is intrusive igneous rock. I think this is igneous rock. The crystal structure is really, really fine. I think this is an extrusive rock. I think this might be an example of basalt. I'm not certain on that at all. Granites are intrusive, basalts are extrusive. You see this one has overall lighter color to it. This one has a darker color to it. I believe this one is more mafic in its nature. This one's more felsic in its nature. All right. Two more things for us to look at today. One is called partial melting. Okay? So I want you to imagine that we have a mass of solid rock, and conditions of the earth are changing so that its temperature is gradually increasing. And the rock is made of all sorts of different minerals, right? A rock is a collection of different mineral grains together. And some of those minerals have lower melting points than others. And so if this rock gets hot enough, some of those minerals will start to melt, and you have little pockets of melting going on within the solid rock. This is called partial melting. If you look at the overall picture, our majority of this is solid rock with small bits of liquid. Now we can flip that around a little bit, and let's say that we had a more widespread melting. So we've taken a mass of rock and we've melted the whole mass of rock. But now conditions change and we start to very slowly cool it down. And again, different minerals have different melting points. The opposite of melting point is freezing point. So the freezing point is really the temperature at which they start to crystallize. They start to line up and form a solid. So let's imagine I have a mass of liquid and it's cooled just to the point where some of the first minerals, the hardest to melt minerals, they start forming back into a solid. And so we get little bits of solid forming within the mass of liquid. This is called fractional crystallization. Fractional, a part of the material is crystallizing. But you may have lots of other minerals that are staying in a liquid form until this cools further. So between these two, when you look at a rock, you can get some ideas as to the history of that rock. If a rock turns up on the surface of the earth and you see this rock that's made out of minerals with relatively low melting points, and then you crack it open and inside you have these little crystals of materials with higher melting points, you can say that, oh, hey, this thing was all melted at one point in time. It went through this fractional crystallization. It went through a long period of cooling inside the earth. Going back to this other one, you may find a rock that's made out of higher melting materials, and you crack it open and you see these little crystals of lower melting materials inside. And that may tell you that, oh, at some point in the past, this the rock warmed up enough that it melted little bits of this and then recooled and formed those crystals of the low melting materials inside. We get some idea where this rock has been over the last billions of years. So that's what I wanted to go through for today. You're going to have a reading assignment and a little worksheet to do. Just a multiple choice worksheet, shouldn't be too bad. Keep in touch. If you need help, let me know.